Welcome to module 55 of Database Management Systems course in the IIT Madras online BSc program. We have been discussing about backup and recovery. In the last module, we have discussed about operation logging, which supplements the log based recovery and provides a complete scheme for recovery, and we outlined few issues which should be taken into consideration while planning for backups. In the last module of this week on backup and recovery, we will talk about RAID, redundant array of independent disks, which I am sure all of you have heard the name of and might wonder what kind of benefits it can bring us. So, RAID is redundant array of independent disks. When it was introduced, it was called redundant array of inexpensive disks. Over time, it is not always inexpensive. So, both the terms redundant array of independent disks or redundant array of inexpensive disks are used alternately, but more often we will just call it RAID. So, why do we need such a disk organization? Our basic motto or motivation for RAID is to manage a large number of disks while providing a view of a single disk. So, actually there is a large number of disks, but when you look from the point of view of the CPU or the system writing to that disk, you view it as if it is a single disk. So, these multiple disks in parallel provides high capacity, that is, you can, since there are multiple of them, you can have high volume of data stored there. It provides high speed through different possible parallel architecture that is adopted in different levels of RAID. Importantly, it provides high reliability by storing data redundantly. Right. Please do not get confused. We have since the beginning talked about the fact that redundancy is bad. That was redundancy which was logical. That was redundancy in terms of your entities and attributes. But here we are talking about redundancy in the sense of having multiple copies of the same data, so that when one disk fails, if it does, then the data can be recovered from the other disks which are still working fine. Right. So, obviously, you should note at this point that the chance that some disk out of n disks will fail is much higher than the chance of a single specific disk fail, but the RAID helps in the way that if that specific disk which has a lesser probability of failure, if it at all fails, you lose everything. Here, by providing parallel array, you are naturally having the condition that some disk might fail, but you will still be able to recover. So, just back of the envelope kind of computation, if you have a system has 100 disks, each with MTTF, minimum time to failure, being 100,000 hours, approximately 11 years, then the system will have 1 by 100 of that as an MTTF, given that at least one disk fail in the whole system, that is about 41 days. So, that is not very, very high. So, but the techniques for using redundancy to avoid data loss is critical with large number of disks, which are required also for scalability, that is higher capacity and high speed. I already discussed the meaning of I in the acronym of RAID. Now, there are three major techniques, primary techniques, which are independently or in a mixed form used to achieve different types of RAID levels. The first is called mirroring. Mirroring, as the name suggests, also it is at times called shadowing, it is basically keeping duplicate copies. So, you store extra information that can be used to rebuild the information that is lost in a disk failure, right. So, that your mean time to data loss and mean, which depends on the mean time to failure, can be less, but your mean time to repair would be very, very fast. So, what mirroring does in principle is something very simple. You duplicate every disk, and when I say duplicate, it is not necessarily that it will have to be 2 copies, it could be more than that also. And then the logical disk consists of 2 physical disks, that is the minimum of mirroring, right. You have 2 disks copying the same data. So, when you carry out a write, it has to be done on both disks, and read can take place from either disk, right. So, read can immediately becomes much faster. Now, if one of the disks in the pair fail, data is still available in the other. So, the data loss will occur only if a disk fails and its mirrored disk also fails before the system is repaired, right. So, the probability of that happening is very, very small. So, except for dependent failures such as you have catastrophic failure like fire, building collapse or electrical power surge or things like that. So, the first technique we will use is mirroring. Second is called striping. So, as we have stripes on the shirt, so it is like that. So, what you do is instead of keeping the entire data unit in one disk, you split and spread it over multiple disks, and you can do that at bit level, byte level or block level. In bit level, what you do, you split the bits of each byte across multiple disks. So, assuming that you have an array of 8 disks, you write bit I of each byte to disk I, right. It is all distributed. So, on a failure only one bit can be affected, but not everything. Now, there are flip sides. The access can read data 8 times at the rate of the single disk, because you are reading from 8 disks together in parallel. So, that access would be fast, but the seek and access time would be worse than a single disk, because you will have to do the seek on all 8 disks together, right, through the controller. So, bit level striping has been an idea, has been used, but not used strongly anymore. You can do the same thing at byte level, divide the file into bytes each, and say suppose you have 4 disks, then you write the first byte on the first drive, second byte on the second drive, third byte on the third drive, fourth byte on the fourth drive, and fifth byte you again write on the first byte. So, you can easily have an expression which says which drive it goes to. So, again you do things in parallel, but you are doing it at byte level. So, you have a better trade off in terms of the volume of data that you can read in parallel. This is used, but again it is slowly getting limited. What is more common is doing a block level striping with n disks. You write block I to the disk I mod n plus 1. I mean, so if you have the block 0 goes to disk 1, block 1 goes to disk 2, and so on. So, the request for different blocks, you know block is the basic unit in terms of which we request. We have already talked about that several times. So, request for different blocks can actually run in parallel if the blocks reside on different disks, right. Of course, some blocks after n it will fold back to the first disk. So, some blocks will be on the same disk. So, a request for long sequence of blocks can utilize disks in parallel, right. So, striping is a way to, like mirroring is a way to increase redundancy and therefore reliability of the system. Striping is a way to increase the parallelism at different possible granularity. The third that you use is again for correctness. You use a parity. you know about order even parity. So, you take say a unit of data, say 1 byte, you add up the bits, and as you add up the bits, you put an extra bit. Suppose you have 0, you have 0, 1, 1, 1, 0, 1, 1, 1. So, you have 6 bits. So, you add a parity bit, which is 1. So, which says that this will always become odd parity, right. That is, the number of ones in the entire representation, 8 bits and 1 parity bit would always be odd. So, in contrast, if you had this, then you will add a 0 parity bit to keep it odd parity. Similarly, you can do even parity also. So, naturally, the consequence is if one bit flips, suppose this becomes 0, 1, 0, 1, 0, 1, 1, 1, 1, then this data becomes even parity. So, you can immediately know that an error has occurred. So, that is what is called error detection. So, that is what normally would be available, but since this is known as to which disk is failed, because that you get to know independently. Since you know that this disk has failed, so you would know that from the parity information, it is not only that you will know that detect that 1 bit error has happened, but you can also correct for that error. To recover the data in the damaged disk, you XOR the bits of other disks, including the parity bit disks. So, that is how. So, you can have a parity of with bit interleaving, or what is more common these days, you can have it at the block interleaving. So, parity is another way, which is lot more I should say lot more compact and less expensive in terms of storage compared to mirroring, which is a smarter way to actually find out if there is some error that has happened and to correct for that error. So, these are the 3 basic techniques that you have, and given that combination of these techniques give you different types of RAIDs called RAID level. So, these are different architecture that you use. So, which employ techniques of striping, mirroring or parity to create reliable scalable storage using general purpose hard disk drive. The basic advantage of RAID is it does not need a very high quality special disk with high reliability. Those are also exist, but those are a lot more expensive. So, there are a number of RAID levels, RAID 0 which use striping, RAID 1 which is mirroring, RAID 5 which use distributed parity. We will talk a little bit about that. And you can also mix multiple RAID levels through a nesting called hybrid RAID. So, you can have striping of mirrors or mirroring of stripes and so on. Right. These are standardized through certain standard organization into a DDF. Now, the important thing to note is do not think that this is a hierarchy of levels, that is 1 is better than 0, 2 is better than 1 or something like that. It is just a way to identify. There is no metric of performance or reliability that is associated with them. Right. Now, naturally, while these RAID will provide you a good protection against for recovery against different hardware defects, defective sectors, read errors and so on, but they will not give you protection against various other forms of data loss like catastrophic error, which is fire, water, soft errors such as application programming error, software malfunction, malware infection and so on and so forth. So, the thought that you must cast in your mind very strongly is RAID is only a building block to prevent larger data loss, but and provide recovery for that, but it is not a replacement for a backup plan. It has to come along with the backup plan that is already required. Right. So, let us quickly take a look at the RAID levels. RAID 0 is data striping. There is no redundant information. So, you are striping the data. You write A1 here, A2 in the other disk, the 2 disks as you can see 0 and 1, A3. So, odd ones are written here, even ones are written here, right. So, it has a naturally independent disk. So, the space utilization is 100%, whatever disk you have, you are being able to use anything, you are not keeping any redundant information. So, it has a best write performance because you can at least write 2 disks in parallel, and certainly it is the least costly, but the reliability is of course poor because neither you are using parity nor you are using any kind of mirroring, right. So, that is RAID 0. We will see in what context which kind of RAID level will be used. RAID 1 talks about mirroring. So, it is the most expensive solution, and it is one of the most expensive solution I should say, and it has excellent fault tolerance. So, what you do is you simply replicate the disk. So, you can see that you have again 2 disks, you are not striping the entire data you have on disk 0, you also have it on disk 1. So, 2 copies exist on different disks. You can distribute the reads between 2 disks and allow parallel reads wherever possible, and it does not stripe the data on different disks. So, the transfer rate for a single request is comparable to the transfer rate of a of this disk array is comparable to that of a single disk, but the space utilization as you can see is 50%, right, because you are keeping a 100% copy. So, you need double the space. The RAID 2 uses parity. So, it uses parity for correction. So, RAID 2 will stripe the unit with the striping unit is single bit, right, and it uses Hamming code. I do not know if you are familiar with Hamming code. Hamming code is you add, if you have a 4-bit data, you add some more bits to it in a unique way, so that the entire code, if it has a flip in 1 bit, you not only that you can detect that, which you could do in a normal parity also, simple parity also, but you can also figure out what is the particular bit position where that flip has occurred, right. So, it is single error correcting, double error detecting code, right. So, what it needs is, it depends how many bits you will need for this parity depends on how many bits you are trying to code. So, if you have a 4-bit data, you need 3 additional bits to be added. So, here the illustration is with the 4-bit data. So, these are striped A1, A2, A3, A4. So, 4 bits are striped on 4, and then you have 3 parity bits AP1, AP2, AP3. These are the Hamming bits which you spread. So, you have 7 disks over which the striping is happening, right. So, if you have a disk array with D data disks, then the smallest unit of transfer for a read is a set of D blocks, right, because you can do that in parallel. And for writing, obviously, you have to modify D plus C blocks, where C is the number of check disks. These are the check disks, as I said. So, those additional, like here the example is shown in terms of 4 bits of data and 3 bits of check. There is a, if you understand Hamming code, you will see that there is a very structured formula to decide how many Hamming bits you will require. In RAID 3 level, what you do a mix of byte striping with parity, right. So, you use a single parity disk. So, you are doing a byte striping, not a bit striping, right. So, you are writing A1, A2, A3 like this, and then you have a parity disk. In the parity disk, for example, here you are writing the parity of A1, A2, A3. Next, you are writing the parity of A4, A5, A6, write that. So, you write byte-level striping with dedicated parity. Naturally, RAID 3 cannot service multiple requests simultaneously, because any single block of data is spread across all members of the set, right. So, it does not have a very good parallel bandwidth. RAID 4 uses striping, but at a block level. So, it does block striping plus it does parity. So, what it is saying, again you have a parity disk, but now you are spreading blocks A1, A2, A3, B1, B2, B3 are blocks, and these are their respective parities which are kept in the parity check disk. You can obviously at the time of recovery, corrupted or lost data can be extracted by XOR mechanism. If you do not understand the XORing mechanism, you will have to read about the parity mechanism little bit in detail. So, this facilitates that you can recover from at most one disk failure. So, at a time if one disk fail, then you will be able to, using the parity, you will be able to restore that data. But if more than one fails, then you will not be able to do that. So, naturally write performance is low because you need to write all parity data to a single disk. So, that becomes a bottleneck. This becomes a bottleneck because wherever you are writing disk 0, disk 1 or disk 2, you will have to write the parity on disk 3. So, that becomes a bottleneck in terms of writing. RAID 5 distributes the parity, trying to improve on RAID by distributing the parity. So, what it is doing, it is writing the blocks as well as the parity of some block which is in a different disk here. So, there are 4 blocks shown, there are different blocks shown here. So, the parity of D is written here, parity of C is written here, parity of B is written here, parity of A is written here, right. So, when you are reading, you will be able to, you are reading the parity from a different disk, but that is not a centralized single disks, right. So, read requests will have much higher level of parallelism since the data is distributed all over the disks. Read requests involve all disks, whereas the system with a dedicated check disk, the check disk never participate in the reads. Right? So, it allows recovery of only one disk failure like level 4. So, in terms of failure, it is not got anything special. In RAID 6, which extends RAID level 5, you do another parity block, right. So, it is a 2 parity mechanism. It uses another type of code called these are called syndrome codes, Reed-Solomon code, which has 2 parities P and Q, and you write them in 2 different disks. So, for example, for D, the syndrome DP is written in one disk, syndrome DQ is written in another disk, and you will see that all these are distributed. Like for A's, syndrome AP is written here, AQ is written here, right. So, write performance is still poorer because of the increased complexity of parity calculation, because you will have to compute both P and Q both. It uses, as I said, Reed-Solomon code. I will not try to explain that, but if you know. Therefore, it can handle a failure during recovery of a failed disk, right. This is because of this double syndrome, the extended dual parity, it can actually handle up to a second disk failure. So, that is a big advantage of RAID level 6. Now, what you can do is you can also mix these, you can nest them, that is have one level, like kind of stack the whole organization. One level you do according to certain RAID level, and then those RAID levels you connect through a different RAID level. Right. So, for example, say if you say RAID 50, actually 50 is not 50, it is 50 is 5 and 0. So, what it does, it has a lower layer which is RAID 0, that is it will stripe, and it has a upper layer which is RAID 5, which is distributed parity. In that way, you can improve the performance of certain combinations. So, here is what I will just show you 2 examples of hybrid. So, you have RAID 01. So, here is RAID 0, here is RAID 0, here is RAID 0. So, what is RAID 0? RAID 0 is pure striping, but then you are doing a mirror of these striped disks by RAID 1, right. So, you are trying to get benefit of both. Of course, you have less utilization of space, I mean RAID 0 otherwise was optimal in terms of utilization of space, but now you have 100% redundancy on that, but you improve in terms of the reliability of the data. In contrast, if you have RAID 10, then first at a lower level you have RAID 1. Which is RAID 1? RAID 1 is mirroring. So, first you mirror, these are mirrors, and then the mirroring is on striped data. So, A1 is here, A2 is here, A3 is here, A4 is here. Right? So, it provides a better throughput and latency than all other RAID levels except RAID 0. So, that is one of the popular levels. So, there are several others, there are 50, there is 100, several others depending on what all you need. So, the question comes as to, since we have so many RAID levels, so what RAID level should we be using? So, some of the characteristics like RAID level 0 is not fault tolerant. So, if you need fault tolerance, you will not use it. So, you can see one criteria being used is whether it is fast, one is whether it is fault tolerant, one is whether it is cheap. So, RAID 0 falls on here, which is fast and cheap, but not fault tolerant. RAID 5 is fault tolerant and cheap, but not fast. RAID 10 is fast and fault tolerant, but not cheap, like that. Right? So, different such choices can be made depending on what you need, depending on the monetary cost, the performance, the IO performance, performance during failure, performance during rebuild. So, there are three performances we are talking of. One is during normal operations, which is obviously most critical. But what is the performance during failure? What is the performance when you are rebuilding the disks after failure? Right? So, RAID 0 is used only when the data safety is not that important. 2 and 4 normally are not used because they are subsumed in 3 and 5. They are simpler cases than 3 and 5. 3 also is not used because bit striping forces a lot of single block reads. Right. RAID 6 is used rarely, since level 1 and 5 offer adequate safety for most applications. So, the choices are, but of these obviously commercially we will not get all kinds of RAID levels available today. Right. So, for example, RAID 1 level 1 is has a much better write performance than level 5. Level 1 has higher storage cost than level 5. So, these are the different trade offs. I will show you a summarized table talking about all that. So, there it can compare the RAID levels in two ways. One is the current table, which I would say more theoretical. So, here the basic 7 RAID levels are being compared. What is that, and what is the minimum number of disks, what is the space efficiency in terms of, if you are using n disks, how much of the disk you can use. For example, RAID 0 you can see is certainly 100% because you are not copying anything. RAID 1 is 1 by n because you are making n copies of the data, and so on and so forth. These are little more difficult to analyze, and you can see what is the fault tolerance. Naturally, in RAID 0 it is none, no fault tolerance. Here it is n minus 1 because you have n copies, whereas in most others it is 2, 1, and in RAID it is 2, and so on. So, given that, I mean that is good for study understanding, but what we will be more interested to look at is what are the practical comparisons. So, you can now see that I am not talking about all RAID levels because they are not popular, they are not manufactured also. I mean most of the like 2, 3, 4 these kind of RAID level disks are rarely manufactured these days. So, what is important is you can see we have already talked about the fault tolerance, the performance, and so on, and the capacity utilization. So, based on that, what you should focus on is looking at this last row, where we are talking about what kind of application will use this. RAID 0, what is the characteristics? No fault tolerance. Read performance is high, write performance is high, capacity utilization is 100%. So, you have higher end workstations, data loggers, real time rendering, but very transitory data. You are not so concerned about the persistence, but your performance has to be the highest. You will use RAID 0. You will use RAID 1, where you have a single drive failure protection. you have medium performance, 50% utilization for operating systems, transaction databases, where you need a balance between safety and fault tolerance and performance, right? And you don't expect the data size to grow really that large. Whereas when it comes to, say, data warehousing, web servers or archiving servers, you need a very high capacity utilization. That is very, very important, because they are very, very large. So, you cannot keep on spending money on having extra storage. Single drive failure is fine. Low performance you can live with, because warehousing is mostly an offline or semi offline application. When it comes to data archives, backup to disk, high availability solutions, large capacity requirements, you will probably go for RAID 6. It gives you the big advantage of having 2 drive failure protection. One of the most common for fast databases, file servers, application servers that we are studying about is RAID 10, which has up to 1 disk failure in the sub array, has a high read performance, which is what you need, a medium write performance, and you have to live with a capacity utilization which is 50%. So, keeping this in mind, you can decide on what kind of RAID you want. And finally, before we close, please keep these points in mind that RAID does not equate to 100% uptime. No system can guarantee you that. And RAID does not replace backup. It does not protect against data corruption, human error, or security issues. For these two, you should have a robust backup plan. And RAID also does not necessarily allow dynamically increasing the size of the array. It is not easy to just plug in some more disks and increase your array. You have to rebuild the RAID. So, it takes time, and it is also not the best option for virtualization or high availability failover, which are provided by other solutions like system by SAN or NAS and stuff like that. So, with that we come to the end of this module. We have taken a look at the high performance, high reliability, high capacity disk arrays built out of ordinary disks, RAID, which will be very useful in terms of our overall backup and recovery scheme and for our total database hardware design. Thank you very much for your attention. See you in the next module.